Okay, we will now talk about calculation for cross curves. See, nowadays with computer available, calculation has become very easier. Okay, early days there used to be a number of methods, I mean, ingenious methods and instrument device, because as you can see, the number of calculation for that is quite large. If hydrostatic calculation, uh, you required number of stations, number of water lines, but no number of angles. So this is like doing hydrostatic for number of angles. If number of angles is 15, that means like 15 times hydrostatic calculation you are doing. The amount of calculation is of that type. So obviously there have been many ways of trying to do the calculation. The problem of another problem is that supposing I want to find out this, you see, under the water line. Now what happens? I am having offset table with me at equal water lines. I normally I am having this offset table, but here I want to find out area under this curve. How do I find out? So it becomes a tedious thing. I will have to actually from here find out, divide this in some number up to this point, maybe in some number of divisions, and pick up, you know, this distance, this distance, this distance, this distance, etc. See, each one. Now again, what is happening is that for each station, normally I have an offset. What is offset? Offset means I have got y values at fixed interval of water lines, you know. But here that concept cannot apply anymore, because this line, this particular line, do not fall on water lines, first of all. Second of all, my ordinates are this much. I mean, if I draw another one here, see, my ordinates are actually this. Okay, so you can imagine immediately that the calculation become even more difficult, because I have to actually draw a section, divide that, pick up by measurement of the scale these particular lines, okay, you know, and then use the Simpson's formula. Now not only that, I have to find the moment about this line. Moment about this line can be of course found out. Again I have to take, supposing this is my y here, I have to take center of that and multiply. I will come to this part in a minute, but we have to not only find this ordinates, you have to find the center of the ordinate and do the calculation, and you have to do that for each station, for each water line. So you see, the earlier days, this is for historical interest. Earlier days there was an instrument, it was called integrator, by which you could actually find out by taking the knob of an instrument. uh, See, there is an instrument where there is a something like rail, there is an instrument with a point here. If you actually took the point, this point along a curve, you know, you just traced along a curve, there was a gauge here which would give the reading of the area. And not only that, if you, it will also give the reading about some fixed line, some line parallel to the moment about that line. So it was a very interesting instrument called integrator, where you have to take the knob of that instrument and trace the curve like that in a cyclic way. It must be closed curve, and obviously the instrument will move here. There is a gear that would actually turn, and it will give you the area. So this is very interesting. But now question is that, remember, if I do that, I only get the area of a section, but I need the volume. I need the volume of that. That means if I did this instrument also, I have to do for each section, note it down somewhere, then do Simpson's formula. So there should be a better way of doing that. So here, this particular rule we did not talk. There is a integration formula called, I must mention this Chebyshev. You probably know this Chebyshev rule. See, remember that all these curves, that when we do y dx, this gets replaced by something like this. I mentioned that before. Now Chebyshev's rule is the rule which is unique, where all these are made 1. You cannot make this 1 so easily unless you choose the y to be at some unspecified location. That means if there is a curve here, see, Now what happened, what Chebyshev did is that there are Chebyshev ordinate, that if you take the ordinates at this location, this location, this and this and this, then the integration becomes simply addition of this. In other words, the integration is written such a way that the weighted sum, the weights are equal to 1 provided the y's are taken at certain given locations called Chebyshev's ordinates. The theory behind that I am not going to go. What the point is also same way. You see what happened, you assume that this is a polynomial curve. Okay, now you assume that if being a polynomial I must have this weight sum of this. Now you want to find out where must my these y's be so that my w's become 1. This is how it was done. And now if you know, for example, this might see, suppose this is -1 to +1, so this distance might become 0.7821, this might be some odd number. It has been found out that if you take the station spacing at that location, then if you just add them up, you get the volume. So they are not conforming to the standard ship stations. See, supposing in this case, it is found out that if you take at this line, this somewhere some these Chebyshev's ordinates, then if you take this the values here and here and here and here, if you add them up, then you get the integration over the length. Okay, now this concept becomes very useful. This is called, again if I write it, ordinates. So what happens is that in using the integrator, if you could find out, if you could draw the stations at the Chebyshev's ordinates, that means you have here a typical stations done, number of them. See this, you have to draw the full one. Here you cannot draw half one. If you draw the stations at and you now take now an inclined line here and take your instrument here and take the instrument round. See, you have to find out actually under this water line. Okay, so what we will do is that, see, this is the interesting part. You take the instrument here. Now first you go around this round, then you come here and go around the next one, then you come here and go around the next one, then you come and go around the next one. In one shot, by going around very slowly, you get directly the volume reading. This is the most interesting part of it, you see. And also you can get the moment in here. What happens, you need the moment about this, actually this kn becomes if you this k2 and here you can get directly the kn, because it is nothing but if taking moment about a line perpendicular to this, and this instrument is such that you can set it where you can also get the directly the kn. That means by going to this like this way and keeping the axis in some fashion, in just one shot you could get this volume as well as moment of volume and kn. Why I mention this is that this is of historic importance. These instruments are now obsolete practically. We have one or two, so 40 years back people used to use, even we use some 20 years back. But the point is that everybody should know it, because this is something unique for naval agriculture. Today nobody will think of using this because the accuracy is not good enough. You will always use some computer program. I will discuss one method of computer programming, because today you can do a million calculation in 1 second in a PC. Okay, those days it was not possible. You have to do this calculation. This is why it was there. So we just know this, but as I said again, this integrator is completely obsolete. Nobody will think of knowing it. But I think as a course we should at least say we have heard this instrument. That is why I mentioned this. It's a unique instrument. Actually it is gear based one, and if you go around one particular thing, see, this gears will just rotate to the extent proportional to the area. There is a teeth here. See, as you go around, the teeth will rotate. If it is larger area, it will rotate more, and this rotation is exactly proportional to the area covered.
So here, when you are going to the second line, so that this will give
no. See, here you go this much, then you go here and go this much.
Okay, then you get the difference.
Yeah. See, actually, if you now not difference, add it. See, if you the idea is like this instrument. If you go like that, it will give you the area under this. But if you now go, see, here to here and go like that again, go up to this, it will give the area under this. Now if you go from here again and come back to here, it will give the area under this.
Each time you're going on a different plane.
No. You're not going. How you are going in a different plane? No, you're not going because see all the sections are under this water line.
So then why you have to go on 4 lines? You can just go on the outer skin and get the complete
Which outer skin?
that is the hull.
Now that's what you are doing. No, you're see you have to find out. No, let me draw this another. See, this is a section here. Yeah, let me draw just two section. Okay, this two section. Now you have to find out this area plus this area and Simpsonize them. Now the way these sections are Chebyshev sections, so the volume is equal to this area plus this area, straightforward. See, these are Chebyshev's ordinate, so the volume is equal to area under this plus area under this.
So again, two different planes.
No, they are drawn in the just like what you have done. See, it's like a body plan. You just draw the body plan, but not at the stations, but at Chebyshev's ordinates. So you are redrawing the body plan at Chebyshev's ordinate. So this is a two-dimensional piece of paper only. See what you would have done otherwise. You would have found out this area, write it down. Find out this area, write it down. Like that you will do. So here same thing you are doing it, but the instrument, because what happened? See, you start the instrument from here. You go and come back to this point. You have to always close it. To get the area. So if you have come up to this much, you get the area of this much. Now again you start from the next one from here, go up to this, come back here and come to this point. So you got the area of the next one. That got added because the first one area is already stored. It has rotated so much, say some reading is there. Now this getting added on that.
So it is, I mean, adding it to
Cumulative, exactly. It is cumulative. Therefore, now in the next one you again go to the next station. So what happened? If you go carefully, you see the entire lever reduces just to one set of going to the entire station. You will directly get the volume and also the moment. Yeah, this integrator is actually level higher because it does area and as well as moment. That is why it is planimeter is nothing but a simplified integrator where it does just area. Here it is area plus moment, as you set that for the moment you can set an axis. So this axis will be set actually because you want to find the moment about line perpendicular to this. See if you can find the moment about this line of this volume. See if this is the axis chosen through this k, then you will get directly the moment, and if you divide that moment, then you get the kn directly, or rather this transverse distance. From there you can get kn. This is the idea. The full idea is that. But as I said, these instruments are very obsolete. There is not you don't use them because the accuracy is not good. Only those earlier days when you could not do the calculation. This is a time of we are talking of a time when there is not even electronic calculators. Probably not even slide rule. Just even before that, it's 1940s like that. Just for historic interest, I am talking. But let us see today. What will you do? See today, if I have to calculate, what I would do. Now, the method I am going to be telling is a very unique method. You will not see that in any standard normal book because it is very appealing. There are many methods there. You see, typically what happens, now this we understand. Typically, we will be having these ordinates known to us, offset tables given to us, isn't it? See, this is water line. This I am drawing at equal intervals. This water lines. See, yj offsets normally are available to a naval architect in a tabular form or in some form. You would want to use those numbers in a computer program. You don't want to actually pick up. See, if I have to now, suppose I have this line, if I have to now go and measure by a scale and feed them, it is a tremendous job. Earlier days we were doing that, but what I want to tell here is a method where offset becomes the input point, which is already there for your hydrostatics. You don't have to do any work extra. Now how we do that? The interesting part is like this. Suppose this line is, see, this is my let me put this same way, this is y, so this is z, right? So z equal to, or we will put it as y equal to mz plus c. This is a equation for a straight line. This equation y equal to mz plus c. Actually, m is nothing but tan theta. You can easily find out this expression in a computer program. You can actually find out, because we can easily find out where the intercept is, whatever, just through one point. We can find out this expression in a computer program just like that. You know, m is nothing but tan theta, and c can be any number. Uh, Depending on what number c, the lines are different lines. See, if you have a line here, then c will be say 5, etc., etc. So it is all known. Now what we do is that, see, now supposing at any height, this is, let's say, given height z is a water line, 1 meter, 2 meter, etc. Now at a given height z, my half breadth is y, say, let me call this yj. Now I can find out what is the intercept on this line by putting this expression. Let me call this the y bar j. Now then y bar j equal to m into that zj plus c. Computer program, I can find it out. Now let us see carefully. See, I have this line equation known. Okay. Now I take a given water line. So at this water line, I know this. This is my offset table. Say 1 meter, I have z equal to 1 meter. I have no offset table. Z equal to 1 meter. I find out what is the intercept here from this equation. I just put that, in this the z value to be 1 meter. I will get this y. So I have got this. Now what I will do is that, see, that if yz bar is more than yz, in actually yz bar is negative number, we will get, you see. Now let us see if minus yz bar, because yz bar will be negative number. If this is plus 2 meter, this is going to be minus something. Now if minus of that, that means the absolute value of this is more than this, then I will say my ordinate here is equal to this much. I will say my ordinate is equal to 2yj. Okay. On the other hand, if it is less here, I will check. Now if minus yj is less than yj, that means somewhere here, then what I will do, I will take ordinate equal to yj plus yj bar, or plus or minus yj. This will be minus because of this, whatever. I mean, I will then take this plus this. Now if it is here, okay, when I find out that yj bar is positive now, and it is less than the other one, then I will take simply this part. And when I find that yj bar is more than this, see, at this location, okay, then what I will do, I will make it 0. So I will write down in the next one, but it is a very interesting concept, you see, by which you can actually recreate, taking the equation of the line, the at that ordinate levels, the exact ordinate under these lines. You see, this requires a little more discussion, because there is a lot of other issues will come. See, we will just do very crudely here. This water line is here, water line is here, water line is here. I have this line here. So you see here, what we have done is that we could find out here this much. So we have this condition. Remember that this case, this point A, yj bar, this is my yj bar, remember. This minus of yj bar, let me, no, yj bar is negative. So minus yj bar is more than yj. So we have got ordinate equal to 2yj, this much. Okay, come here. Same thing, I will find out that my yj, this is my positive yj, is less than yj bar is less than yj. This is my yj bar, remember, this is yj bar less. So my ordinate is equal to yj minus yj bar, that is this much. Now I come here. Here my this much is my yj bar. Remember, this is my yj bar. Yj bar is more than yj. Ordinate is 0. So I have got here 0 ordinates. I have got here this much here. I have got here this much. Like that I proceed. So what happened? I have got, now this is very carefully to be seen. So what I have got is that I have got a Simpson's rule with a 0 ordinate here. I have got an ordinate here, I have got an ordinate here, and of course if I go down, I will get all ordinate here. So I will be getting a curve. If you integrate, I will get a curve integration of this curve. Okay, but it is not exact, because what happened, I have not been able to uh, sort of pinpoint this point. No, neither can I pinpoint this point. So I will have an error connected to this, an error connected to whatever this, because I am not able to exactly pinpoint that. Now what I should do? I should try to reduce that. Now how I can reduce? It's very simple. If I could take this ordinate at a very close grids, supposing I take 100 on this, let us say. If I took y at very close grids, the ordinates, then I can easily find out, and this area will become, now you see, here, so small that it will be negligible. The question is, therefore I must get small ordinates. Now you will ask, anybody will ask, but where will I get? Because I have got only at 1 meter interval my y's. Now here comes the unique thing, is that in any computer program, remember that whenever I have done these ordinates, I have presumed that they are actually uh, polynomial. Therefore, I can write another computer program that in this part, for any given g, I can easily find out this. That is just in a computer program I can very easily write down. In fact, one can show that if you take, it is seen that if you take just 4 of them, just like at 0.25 meter interval, it gives more than correct result. And for that, if you want to take 4 of them, you can actually don't have to interpolate. You can write down y at c is something like, again I should do this way. See, if I call this to be y1, y2 and y3, and if I want to find out this, you see this, I call this to be, say, y1 by 4, then say y1 by 2, etc. It will turn out that y1 by 4 equal to some number into y1 plus some number into y2 plus some number into y3. This is all available in a standard textbook, standard finite difference book. You don't even have to write a program. If of course somebody is more wants to be more exact, then you can easily find out a polynomial a, b, c and just fit it. It doesn't take any time at all in a computer program today, no time at all. So this way what happens, if you do this way, then all you have to do is to feed your just offset table, nothing else but offset table. And you see it becomes automated. You have an offset table, so you start, another question will come, you start this line, you see now there is this line there. So let us say I will start the line from this point, then you will find out that I will fit this mx y equal to mx mz plus c. I see that when z equal to 0, y equal to 0, so c becomes 0. So this line becomes y equal to tan theta into z if it goes to this point, 0, 0 point. Okay. So now I can use the next line where I know that c will be this much. This is nothing but, if the waterline interval is taken to be 1 meter, this is nothing but 1 into tan theta. What I mean is that you can very automatically create these lines. See, maybe it is not clear. Probably I should see. This is again the case. Now I have to recreate the line. So I have a line here, first line here. Now this line is y equal to mz plus c. Now you see, this is my y axis, this is my z axis. Now at z equal to 0, y equal to 0, this gives me c equal to 0. So this line is y equal to mz plus c, that is m is tan theta into z, the first line. Okay, so I did that. Now in a computer program I have to go for the next line. Let us say the next line is this one. Now in the next line we will find out that at z equal to 0, y equal to this distance. Say this distance is, say, y bar, let me say. That will tell me that c equal to y bar if you put it here. But how much is y bar? Now question is that you have chosen a line which is this, the difference between the two is, say, d z. Let us say, you are taking these water lines at dz meter interval. So if this is dz, this is theta, this distance is nothing but dz into this, I mean dz sine theta, whatever, I mean you can find it out, dz by sine theta. So this distance therefore is easily known from here. So therefore in the program you say that my water line will start from y equal to I equal to 0 to some number at interval of dz of 1 meter, and I can, for each one I can just loop through. I can have one loop where first line is chosen and find all these things and integrate them, second line is chosen, etc. So it becomes very, very automated. You see, This is a method that was suggested, not very popular, but one of the good methods. I will tell about other methods. Nowadays there are so many computer methods, there is no problem. Now a goodness of this method is also that sometimes you have a section like a bulb, sometimes you have a section like bulb here. Let us say there is a, I mean there is an excited station, but let us say there is a section. Now you might have a water line going like this. That means you might have some place this thing, then some place nothing, and again some place this thing. But if you use this method, automatically you will keep on getting this, then keep on getting zeros and keep on getting the numbers. If you go up to the entire extent, you will automatically get the ordinates. See this, etc. going to 0, 0, 0, 0, 0, and keep going with the number. It does not matter that there are zeros here. Let us say there are 200 points, Simpson's rule, 200 operation. It will not take any time, no time at all. So you don't worry about, I mean, we don't worry about the number of computing. We simply add the entire thing. So this is one of the feature of that. Now let us see how to find the moments that I did not sort of discuss. Now see for moment part. Now this is my line here. Okay. So when it is this line, I know this distance. See this is my ordinate. Now moment about this line, ordinate is going to its center is going to be here. This particular thing, ordinate, will have a center at the halfway through. If this is ordinate, then this ordinate by 2, ordinate by 2. Okay, how much will be this much? Obviously, this is my yj minus ordinate by 2. You see, so this distance is going to be yj minus half ordinate. Whichever way you do that, you can easily find out this halfway. Question is that, see, for example, if I take this, in this case, this is my yj bar. So the half of that is yj bar plus, I mean the distance of this center is yj bar plus half ordinate. So like that, the center location, that is the location of center, if I call this h can be found out again in one line for the various condition, and the moment about that is nothing but ordinate into h dz. See, when I am doing Simpson's rule, if I take the ordinate and use Simpson's rule, then I get the area. If I take the moment of the ordinate about this line and Simpsonize them, I get the transverse volume. Okay. And if I take the moment of this about this line, that is, if I call this to be say v, if I take ordinate into v into dz, then I get vertical moment. I am only trying to show therefore the very basic principles here. See that if you write systematically, if one is able to write systematically, the condition, maybe one of them we could do that, in a big drawing number of diagrams. See, so if I write that, I can actually tell this distance is how much. This distance is, for this case, yj minus yj bar, because this much is yj, this is yj bar. Distance h, this is my h. Okay, so h in this case is yj bar plus half of yj minus yj bar. Yj minus yj bar is this, half of that is this plus this. So we have got this. You take point here, this is my yj, this is my minus yj bar, because I am taking minus because it is this thing. So we have got here same thing, actually the same thing will apply. The ordinate becomes yj minus yj bar, and the centroid is half of that here. Okay, so we can do from the other way around. We can say yj h equal to yj minus half of yj minus yj bar. Like that we can do all of them. So like that we can find out, and of course vertical one is very simple. Vertical one is simply the height, this vertical height. So you see, in one shot you could actually find out the ordinates here, and you can do the program, the penalty that you are giving is only that you are not able to exactly find out this. But then you are making it so small, it will make no difference at all. Okay, see this is one of the method that was appealing to me, but there are many methods nowadays. See, one can do in a computer program, even actually, uh, you know this equation, people can try to find out this intersection point. You can find out these intersection points. Having found it out, you can actually use, there are so many methods available, you can actually divide these in number of ordinates and find out exactly values here, and this part you can do from hydrostatic, etc., etc. There is no hard and fast rule today, that depends on ingenuity of the person who is writing the code. Now it is, in fact, in offshore structure, it has become common not to do cross curves, but this, I was telling that iteration, that if I want to find out this WL line, you cannot hit it, but you can do number of calculations. You assume here, go up, down, even that can be done very easily, because the computability has increased such an extent that everything comes in a few seconds, in fact. So there is really vast changing of this computing based on what we have today, resources today. In fact, I will tell later on about a pressure integration techniques, where if you have this surface discretized, you can even use that information. So there is a whole lot of methods available. Nothing is so unique that you have to stick to that. Okay. Uh, some of the earlier books used to actually have this wedge method and all. There was a method called wedge method, where you try to find out this area, the difference between the two, and then shift it slightly, etc., etc. There were a number of methods there, but for a course, it is not important for us to know all the methods, as long as we know what is to be calculated. So as I said, we know now that what we need to calculate is area under that and the two moments, and add them up. So I mentioned two methods. One is a very old integration based. One is this more new method based on or half breadths given. I think we will not dwell on that any further. My intention is to tell you what is to be calculated, not how it can be done. Since the how part is now enormous, you can actually use a spreadsheet and actually go around that and find the number. You see, you can draw in AutoCAD. You can just, there are so many software, you can actually trace this, mark this up, and get the area and the moment. Okay, so one can do that also. So there is no end to it for that. Okay, now having said this cross curves part, okay, now we should talk a little bit about the statical stability curve now. So this cross curve now we have obtained. So this is my cross curves. This is displacement versus Kn for thetas. So now what happened is that for any particular displacement, if you want to find out static stability curve, simply we draw the line here, find out the Kns. So we have, for a given displacement, find Kn from cross curves. So now we have got, therefore, theta Kn. Now you have to find out Zz. Zz becomes simply Kn minus Kg sin theta. Now theta is here, Kg is given, so you can just fill up in one line, this, just in one line, and so you end up getting Zz curve. That's as simple as that. It is really, this part is really simple. So you end up getting the curve like this. This is my Kn curve. Remember that Kn curve is a function of displacement alone, not of Kg. Zz curve is function of displacement and Kg. How we are doing that? We are from there taking up, down Kg sin theta. See, at every point you take the Kg sin theta. I mean, from there you measure it down. You just lower it down by Kg sin theta. Obviously, that that since sin theta increases up to 90 degrees, so this lowering down in this part increases. this side. So you will end up getting this. Okay. Now this is how you get ZZ. Now once you get ZZ, of course, it is very simple. Now supposing tomorrow I have G raised to an amount GG dash, then what would happen? My ZZ curves lowers down further by an amount GG1 sine theta. Why? Because you see here we have drawn this diagram. This was my G. Uh, uh, this is my force and this is my ZZ. Now if my G goes up to GG1, then my ZZ is reduced by this much amount, and that much amount is C GG dash sine theta, or rather G dash Z, let's call it Z dash, equal to GZ minus GG dash sine theta. When it is raised up, when it is raised down, of course, it becomes plus. See, when it is lowered down here, then this becomes plus. In other words, you can say that if it is up there, GG1 is positive, down here GG1 is negative, it automatically will take care of this. Okay, so this part is very simple. This part of calculation is very simple. For static stability curve, although it is simple, it is something like this. Establishing this curve from cross curves is trivial, one line, but the property of the ship's stability characteristics are contained in this curve, not in KN curve. KN curve is simply like a database. That database is there for a hull, so you have calculated once for all. Now from that you will actually find out for your condition what is my static stability. But that transformation from cross curves to static stability, that I will write down here. This something has come here. See, cross curves is unique for a given hull. That is purely geometry dependent. Okay. It is computer, you can say large computations. Number of computations are large. You have to do a large number of computations to establish that. But once you establish that, from cross curves going to static stability curve, this is actually specific for a displacement and kg. This part calculation is trivial. Very simple. But importance of this curve is what is there. I mean, nobody wants to know what is cross curves, because if you are to prove your ship is good or bad, it will be based on static stability curve. Its characteristic, how it is good, how it is bad, all that. We will discuss that at length, because this is where whether the ship is good or bad by design actually is stability wise is given by the nature of this curve. You see, this becomes very important, so we need to find out what is the nature of the curve. And actually what would happen is that a ship which goes in different loading conditions with different kg, you have to ensure that this static stability curve has certain minimum basic properties. See, let us see how the static stability curve, I mean today we will discuss only less part. Say suppose excuse me, static stability curve is something like this. First of all, this is ZZ theta. First of all, we recall that ZZ equal to GM into theta. Okay, when for small angle. Now you will see that if you do the d by d theta of ZZ, that gives you dm at theta equal to 0 degree. This is important, at theta equal to 0 degree. So this concept is only at theta equal to 0 degree. In fact, we can go other way around. Better way to do is to say that ZZ equal to GM sine theta. So dgz by d theta dm into d by d theta of sine theta, that is GM into cos theta. Taken as theta equal to 0, this will become GM. At the limit, that means dgz by the exact formula is like this: limit theta tend to 0 is GM. This is my exact formula. You see, what it means is that therefore the slope of this curve, that taken at theta equal to 0, this slope, the slope of the curve is GM. Now what we do normally is that, see, the slope means what? Slope means this by that. If I call this A, this B, this A by B. Okay. So what people do is that, say, remember that this curve is ZZ in meters, some linear length, 1 meter, 2 meter, whatever. So if you make B as 1 radian, make this as 1 radian, then this distance directly give you GM. Most people will tell us that from the ZZ curve, you take a slope there and take 1 meter radian, you get GM, as if this is absolute. But remember that this is not absolute, it is only convenience. Supposing I say my paper is torn here, that does not mean I cannot find GM. I can simply take the slope. I can just take this value and this value and divide them. There is no problem. GM is connected to only the slope of the curve here. That's all. Even if I have this much paper, I should be able to find GM. But only for convenience we do that. It is only for convenience, no other reason. I say this because sometimes there is a notion that you have to take at 1 meter, 1 radian. That is only that if you want to take A by B and make B as 1. That's all. So this is one of the property. The slope of the curve here gives you this. Okay. Now this is an important property. This slope therefore tells me, supposing from you can see from the slope, the curve can actually have a 0 this thing and come up like that. See the nature of the curve this way, this S-type curve, I have already discussed that a little bit earlier, tells me that even if GM is 0, the shape is not unstable. It can be stable later on. See, when GM is 0, it means it is not stable at 0 degree, but it can still be stable at a larger angle. You see, some other characteristic of this curve. This angle is called, well, you can say angle of vanishing stability. That is because obviously the GZ beyond that is become negative. This much distance is called range of stability. Of course, this is the angle where GZ is maximum. We will discuss afterwards that, see, that this nature of this curve is extremely important. I can have a curve which is, say, like this. I can have a curve which is like this. I can have a curve which is like this. Of all these curves, we will discuss later on that it is preferred to have a curve of something like this. It is preferred to have a curve which has an S shape here. That is, it has a point of inflection, and it has somewhere around 30, 40 degree or 50 degree the maximum coming and then coming down, and it must have a large area under that. These things we will discuss, but this S curve part, let me just talk a little bit. See what happens now. This is another thing here. See, this is GZ. Now let us say that I have raised G. What would happen if I raise G? Then the curve comes down by this much. How much it comes down? It comes down by GG dash sine theta. Okay. Now you see what happened to the slope. Here the slope was this. See, my ZZ equal to GM sine theta. Now here my ZZ has reduced to old ZZ, say old minus GG1 sine theta. Okay, this makes me GM minus GG1 sine theta. That means as if my GM has reduced to, as if my GM has also reduced by this much amount. You see? Now, now what happens here? This is interesting. If you think of a line here, okay, slope here, if now G is raised, as if you have pulled it down, as if you have pulled this line down, okay, by pulling the line down, the slope has also come down. Earlier the GM was here, now the GM is here. The slope has come down. Okay, so that's you are pulling it down as if somebody is just pushing it down at every point. Okay. Now what happened? Supposing the curve is S-shaped. This I will discuss in the next one. There are two things very important. Suppose the curve is just like this, not an S shape. Now the slope is this much. You come it down, the slope becomes this much. bring it down, the slope becomes this much, bring it down, the slope is this much, bring it down, the slope is this much. So when this curve is there, and when you make by some means GM negative at 0°, slope has become negative because it cannot, it doesn't have an inflection, it is just a parabolic curve. If the shape is a parabolic curve, moment you have made GM negative, it will completely sink. On the other hand, you say this curve, S curve, you reduce it, it becomes like that. Further reduce it, it becomes like that. You see here? Then what happens? Even though the GM is negative, if the curve is having a point of inflection, this is called point of inflection. Inflection, which means it comes like that and comes like this. It is not, this can only be modeled by at least a cubic curve, at least z is equal to something like theta cube, because if it is theta square, it will be just like this. I will discuss that at a greater length because it has large importance. Then what happens? This curve, this nature is the only nature that tells us the possibility that the ship, even if you make the GM negative, it will have a stability at some larger angle. We will discuss that for a submarine you cannot have an angle of lull, because in submarine the curve is actually a sin theta curve, which is actually something like this. So the moment you make it negative, it will simply upside down tilt. But for a ship, fortunately, most ships are of this type, S type, and you would want it to be that way. You don't want a curve like this, but you want it like this. So we will discuss the importance of this S curve and the characteristic of that, and what makes it S curve, etc. in the next class further. Okay. So today we will just end it at this point. Thank you.
In the submarine, when it floats up in the water.
Then it becomes different. So we are talking about submerged condition. See, when it comes to surface condition.